Hello, everyone. Welcome to my talk about Genie and WebAssembly today. My name is Lee. I'm a software engineer at Snapchat. This talk is about we move a large amount of C++ code originally written for Android and iOS to a web app. So just a few months ago, actually 2 months ago, Snapchat for desktop web was released to public. It brings the familiar Snapchat experience into a web browser app. So the less known fact was that a lot of this internal code in that web app was actually written in C++, and it's exactly the same C++ as used in the mobile apps. The tool we use to bridge our C+ code to the TypeScript web app is the same one we use for binding iOS and Android code to C++. It's called Genie. So what is Genie? Genie is a project originally created by Dropbox. It generates bridging code between C++ and other programming languages. It has 3 parts. It has an interface definition language. It has a code generator, and it has a smart support library. As you can see in the diagram, you prepare this Genie IDL file, and you feed it to the code generation tool, and it generates a bunch of files. And then you compile this generate file and your own handwritten implementation file and your platform-specific code, and you compile everything together, link with support library, and you generate this mobile app. So this is how it was used for the mobile app. The original version of the Genie only supports interfacing C++ with Objective-C for iOS and Java on Android. So here's a brief history of how we use Genie at Snap. Snapchat has started using Genie since 2016. In 2018, Dropbox stopped developing Genie. In fact, they stopped using C++ altogether. So we developed our own version since then, and we're based on the original. We have added a lot of stability and performance improvements over the years, as well as many new features. We open sourced our version in 2021, so last year, on GitHub. The WebAssembly support we developed for our Snapchat web app is the latest new feature. For someone not familiar with WebAssembly, WebAssembly is a kind of code that can be run in modern web browsers, just like JavaScript, and it has some advantage in performance. It's a compile language, so it runs a bit faster than JavaScript. But the focus of this work is not exactly about performance. It's more about reusing our existing C++ code base. Why did we build our own WebAssembly binding tool? There are a few existing tools around, but we have a fairly large code base that is already bridged to our mobile apps through the tool Genie. Having Genie support WebAssembly means we get to use these existing interfaces and existing implementation code with very minimal change. The dev teams are already very familiar with using Genie on other platforms, so giving them the exactly same tool means they have very little learning is required. At the time when we started developing this, the alternatives that I evaluate all have some limitations that made them not viable for our use case. So compared to the alternatives, the other 2 C++ binding tools available for EM scripting, which is the C++ WebAssembly toolchain, and their website, they recommended WebIDL Binder and EM Bind. WebIDL Binder is a bit simpler tool than EM Bind and Genie. It uses another kind of interface definition language called WebIDL, and to define the binding between C++ and JavaScript. EM Bind instead uses pure C++ code to define the interfaces. It is very feature-rich, and it supports almost lots of C++ constructs. Genie's WebAssembly feature in the very low level uses EM bind internally as an implementation detail. We currently use EM bind to forward method calls and performing some of the primitive types marshalling. The biggest reason to use Genie over other binding tool is that it supports web apps, Android and iOS, all at the same time. This actually allows Snapchat to take our existing mobile C+ code written for Android and iOS, and we bring it to our web apps with very little change. It's almost exactly the same code. And another big reason is we generate TypeScript interface output. The other tools, they are only JavaScript, but we will generate very type-rich type definitions for TypeScript. It gives us static error checking in IDE and very nice syntax completion in IDE such as Visual Studio Code. We generate interfaces differentiates nullable and non-null types, so that means you're less likely to make mistakes on this. So we have better support for C++ containers. Genie translates C+ vector sets and maps to JavaScript's built-in arrays, sets, and maps. So in the example, you can see that we call a Genie interface and get strings. We get a list of strings. That is very natural. With embind, they get translated into an object that wraps a C++ vector. So it's less easy to use. As you can see, you call this function, get a list of strings, you get a wrapper of C++ std vector instead of a JavaScript array. So you will have to call some methods to retrieve elements one by one. WebIDO binary, on the other hand, does not translate containers automatically. Another advantage of the Genie interface is that it's very natural to allow you to implement these interfaces in TypeScript. In the example, you can see it really just like implementing another native TypeScript interface. You define an interface that just implements that the Genie-defined interface. And in embind, if you want to implement an interface in JavaScript, you will have to define an object and you call a function to implement that. That feels a bit awkward. It's not as natural as just doing it in the type level. We also support asynchronous methods, which is pretty cool because you can return a future type in the Genie interface. Return here in the example you have 32-bit integer value, and it's a future. That means when you call that method, it does not immediately give you an integer, but it gives you a future, and then you can await on that future in your TypeScript code. In your C+ code, this part is maps to a future type and a promise type, which is very similar to one of the earlier C++ concurrency TS, and it's very closely mimic that interface. So you can just set value and satisfy that future. So next we're going to talk about building web apps with Genie. So the Genie workflow is like this. First, you create some IDO files. You define your interfaces and their methods in these IDO files. You can also define user data types. Mainly, it's records and enums. Records are data, and enums are just symbols for numbers. Then you call the code generator on the command line. Genie has a lot of command line options to customize your output. So we typically would create a shell script called run-genie.sh and put all these command line arguments into that script file. Once the code generated complete, it will generate a bunch of interfaces in your preferred language, and then you can just take these interfaces and implement them in your implementation language. It's mostly C++. Once all the code is written, you just compile everything and link them together and create your final app. So in this example, you can see on the left, we have an interface, an example of an interface. That interface is going to be implemented in C++, hence there is a +C after the interface keyword. The name is interface is my interface and has two methods. One instance method that you can call on the object, and one static method, which is a factory method. You just call it to create an implementation of that interface. On the right, you have we have one record and one enum. The record is just you have name and you define a few fields to specify the types. And enum is very straightforward, very close to what C++ enums look like. We have a bunch of primitive types. These are the built-in types that's supported by Genie IDEO. You can see this. We have bools and a different widths of integers and floating points. We have integer 64-bit integer, which is a bit special in JavaScript because it has to be mapped to big int, not just number. There is a string we map to the standard std string in C++ and the JavaScript string. We have binary to pass non-string integer array, a unsigned 8-bit integer array. We have date types. There are also some composite types that mainly they are containers. For example, we have a list that maps to C+ vector. We have set that maps to a set, an ordered set, and the map that is just an ordered map. We have optional that determines whether a field or a parameter is nullable or not. They map to C+ type optional, std optional. So let's just try it out. We'll just do a live demo of turning a simple, we'll turn a simple, here we can see the examples. We already have this Genie interface defined here that we have a record defines some data which contains only items list, which are a string list. And we have an enum defines how we're going to sort these items. We have a simple interface that basically only has one method that takes, it just sorts things. Then we have some static factory methods. We have a listener object that's going to be implementing our platform-specific language. It has, once the sort is done, our C++ implementation will call this callback interface and notify the UI to update. So here we go. We'll just go to up to the command line and run the code generator. Here we go. Code generator is done, and we can see here we have a generator source directory, and it has a bunch of directory for C++ code, which contains all the C++ interfaces generated from this IDL. And we also have, of course, TypeScript file that's generated. Contains all these interface definition for our TypeScript. And once here I have an Xcode project. I can show you how this compiles after we already generated code for Objective-C, so we can just run it and get a mobile app running. So this is how it works. We can type a few lines here, like line 1, line 2, and we click these buttons. We can sort them with C++. So these are actually calling C++ to sort these lines. Now we're going to turn this into a web app. So we're not going to write any new C++ code. We'll just use the existing implementation code that's already written. Here in this handwritten SRC, that's C++ code that implements the sort. Here we have this C++ class just implements the sort items. That's the Genie interface. And in the other implementation file, it's just the implementation of that interface. Now we're just, I've already written a compile.s for simplicity. I'm not going to use any build tools. I would just use the EMCC compiler directly. It will output textsort.wasm.js. This is the output file name. We use this C++17. We enable exceptions and we enable embind, and there are a few flags that we need to make large integers, stuff like that working, and define some include directories. And then we include all these generated WASM binding files. We include all these handwritten C+ implementation files, and we include all the Genie support library CPP files. Now we can just use this JavaScript to compile the code. So you can see I didn't write any C+ code. I just used the existing ones. Once after compile, we have two new files, text sort wasm.js and text sort wasm.wasm. Now we're just take these two files and move them into to the TypeScript directory here. Here we go. We have this here, and now we can write some TypeScript code to use these WASM files. So this is the TypeScript file. We import the type definitions, and we load this WebAssembly module here. And this is delayed load. Now we just implement the callback interface here, and we define the function sort, which takes a sort order. We grab a few button elements in the HTML document and then bind them to call this sort method. This is just our TypeScript file, and we're going to compile this TypeScript file with TSC. It's compiled, and we got a JS file. Another step we need to do is to bundle it with all its dependencies so it can be used in HTML file. So we got a bundle.js. Now we just open this HTML file. You can see this is a very simple HTML file. In this script line, we loaded the WebAssembly file. And here we create just a text area and 3 buttons. And the last line, we just load our compiled JavaScript file, which is compiled from TypeScript. And that's all. That's already done. I can now run a simple Python HTTP server and just need to find a web browser. Desktop to web browser. We'll just switch to localhost 8000, and I can see this demo HTML. Right, it's already here. We can sort it by different orders and sort random. This is already calling C++ in a web app and works exactly the same as the mobile app. So here I'm going to show you a bit how it was implemented under the hood. The design philosophy of Genie WASM is we prioritize developer productivity over other factors. So the portable C++ implementation, we should work across all platforms as much as possible without changing. Our JavaScript and TypeScript user code should resemble their Java and Objective-C code on Android and iOS so that people can have a very easy time switching to a new language. We use JavaScript native types as much as possible. We don't want to wrap C+ types. We just use native types. We want to reach feature parity with Android and iOS so that everything can be ported over easily without missing features. By crossing the WebAssembly JavaScript boundary, the WebAssembly functions can actually be called directly from JavaScript. If you write a C function, you declare extern C, you can directly call them from JavaScript. However, only that type that can be directly exchanged is just simple numbers. You can pass numbers, but not other objects. But in order to pass other objects, we'll take advantage of that. The address space, the entire address space of the C+ model is an array buffer in JavaScript. It is accessible from both JavaScript and from C++, of course, because it's C++ address space. In order to pass other types, C++ data as a number, and then we access the C++ memory space directly from JS, or we can create a numerical token to the data, and we pass the token That would take lookup. It's a bit slower, but that's, as I said, that performance is not our first priority. It works well enough. We currently use embind to pass basic data types. So numbers can be passed directly. Strings, embind will handle C+ memory access for us. Basically, it will pass a pointer and copy that string into a JavaScript string. Opaque objects is also passed by embind. It's mapped to C++. When it maps to C++, it becomes a val type. embind assigns a token to that object, so it will perform a lookup on in the JavaScript world and find the right object. C++ objects in JavaScript was done implement in roughly like this diagram shows. The JavaScript will hold a C++ proxy object that's generated from Genie, and that C++ proxy object will call the C++ object for us. On the C++ side, the implementation object is held by a shared pointer. So releasing, if you can have multiple references in C++ and releasing all the references in C++ still will not cause the object to be destroyed because it still has an owner as CPP proxy in the JavaScript land. An important aspect is automatic memory management. At the time of this implementation, none of embind and WebIDL binders supports automatic memory management. So if you have C+ object in JavaScript, you have to manually call delete method to delete them, which is kind of not acceptable, not acceptable for our use case. So the way we solve this is we took advantage of a modern feature in recent versions of web browsers. It has a finalization registry. So whenever we create a C+ object, we will register its proxy with the finalization registry. So when the JS object, JS-owned proxy expires, the shared object, shared PTR will be automatically released. When it's gone, the finalization registry will call some core function to release the shared pointer on the C++ side. So that means we don't have to worry about managing memory on the JavaScript side. Another important aspect is we need to retain object identity. That means if we pass the same C++ object multiple times into JavaScript land, they should pass the equivalent check. They should compare exactly the same as the same object. This is done by introducing a C++ proxy cache in the C++ side. When we create a new C++ proxy, it's added to the cache as a weak reference. So when we need to pass another proxy across the border, we will check first in the proxy cache and see if it's already there. If it's already there, then we will pass back the same proxy object so that it will compare the same in the JavaScript. JavaScript objects in C++. We have a proxy cache to manage the object identity problem. Otherwise, it is we have this JavaScript proxy that works as a medium to when the C++ user code can hold this JavaScript proxy via shared pointer and can call the method into JavaScript object. Marshalling data across the language boundary was, as I said earlier, the primitive types are already handled by embind under the hood. We have this for every complicated type, we generate a helper class which manages the marshalling from C++ and to C++. You have both methods that's automatically generated. It's generated in a recursive way, so if you have nested types, like one complex type containing another type, it will be marshaled in a recursive way. there is a special thing, is the box type that is used to manage the boxing of some types, because we can't have integers, we can't have them as directly as value objects in containers. They have to be boxed as objects. So here we go, we can have this redirect this type to another type, so that they can be stored in containers. We also support exception handling, which is actually pretty difficult. We support throwing C++ exceptions into JS, and we also support throwing C++ exceptions through JS and into another C++ block, and we can catch it there and retain all the original exception state. We also support throwing Java exceptions into C++ or through C++ into another level of JavaScript. And in each case, we make sure the error informations are retained. So let's talk about some limitations. JavaScript does not support overriding the default comparison and hashing operation on user-defined types. Because of this, Genie cannot automatically generate these methods for user-defined types. It is possible to generate these for Android and iOS, but not for web apps. And because of this above reason, user-defined types cannot be used as map keys, because the maps are unordered maps in C++, and it needs a hash function. There is no multi-threading support. WebAssembly itself can support threads with web workers, but we currently, the Genie WebAssembly support is based on EMBind, and the EMBind does not work very well across threads. And the last limitations, we require a fairly recent version, like last 2 years version of a browser to run. I suppose for most use cases, at least for Snapchat's use cases, this is not a problem. We just require users to have a recent version of browsers to run our app. Yeah, that's the end of my talk. The TLDR here, Genie can bind your C+ code to browser apps as well as your mobile apps. We have TypeScript output, and that makes consuming them really easy. It is free and open source on GitHub, and it's been actively developed and maintained by Snap. Thank you very much. I think I have some time to answer questions. Yes?